This is an actual example of a Newell car following model being calibrated to trajectory data. And what this example shows is that in practice, we often end up in a situation close to the toy example 3, where gradient-based optimization ends up being effective. So for this model, there are two regimes that are represented by the colored lines here. So yellow is when that particular regime is activated. So the first regime corresponds to the free flow state, and that's when you have a constant speed. And the second regime corresponds to a relaxation state, which is applied after experiencing a lane change. So overall, the model has 4 parameters, the 3 triangular fundamental diagram parameters, and then the 1 parameter for relaxation. So these 2 plots are for the free flow parameter and the relaxation time parameter respectively. So because there's 4 parameters, then these aren't the full parameter space. These are just slices of the parameters around the local minimum. So all the parameters are fixed at the local minimum except for the relaxation time and free flow speed. So I'll change some of the parameters now, and you can see what happens to the model, and you can also see how the regimes are changing as we change the parameters. And I'll do the same for relaxation here. So in this case, the objective will actually be Lipschitz continuous, and that's because the model H is continuous when switching between regimes, but because the partial derivatives of the model have discontinuities when switching between regimes, this leads to the discontinuities being in the gradient only. So again, in this case, the objective is Lipschitz continuous. So one interesting thing is you can see sort of these funny parts in certain regions, and these are exactly corresponding to times when the relative number of time steps in a regime are changing quickly. So for example, for the free flow parameter, if you look closely at the regime the model is in, you can see in this short parameter interval the regime is changing quite a bit, and that's what causes this little blip in the gradient. Similarly, for the relaxation time, you can see there's something funny happening down here. So this is because at 0 relaxation time, then you have 0 time steps of contribution to that parameter. So then when you increase it, you'll go from like 0 to 1, 1 to 2 time steps in that regime. So even though you're only changing time steps one at a time, the relative change in time steps is very big. So this will cause discontinuities that are pretty large. In general, when you're in a more realistic parameter setting around, say, 5 or 6, then you're only changing from, say, 50 to 51 time steps. So then the gradient discontinuities end up being pretty small, and you have to zoom in to see them.